For about 50 years, the story of computing was actually pretty simple. Things just kept getting faster. But what happens when that story just stops? What happens when that relentless march of progress slams headfirst into the hard, cold laws of physics? Well, we're living through that moment right now. We are witnessing a complete rethinking of how computers work, and it's all being driven by one single world-changing technology. Just look at that number, seriously. This isn't a straight line of growth, it's a vertical rocket launch. In less than a decade, the complexity of our AI models has just exploded by a factor of 5,000. This is a demand for computing power unlike anything humanity has ever seen before.
And that's the core of the problem, right? The old rules are broken, but the demand is just getting bigger and bigger. So we need a new playbook. We need a totally new kind of computer. Okay, let's dive into this.
So, to really understand where we're going, we first have to get a handle on the crisis. For decades, making chips faster was, well, kind of a predictable recipe. But our brilliant engineers, they ran into two fundamental physical roadblocks, two walls they just couldn't climb over. First up, they hit what's called the memory wall. Now, the best way to think about this is to imagine your computer's processor is a world-class chef who can chop vegetables at superhuman speed. The problem, all of their ingredients, the memory, are stored in a warehouse a block away. So the chef spends almost all of their time just walking back and forth, waiting for ingredients instead of actually cooking. That delay, that huge gap in speed, that's the memory wall. And we are not talking about a small gap here. A modern CPU can do an operation in a fraction of a nanosecond, but fetching the data it needs from main memory, that can take over 100 nanoseconds. We're talking orders of magnitude slower. Our master chef, the processor, is spending the vast majority of its time just waiting. It's a colossal waste of potential. And the second problem was the power wall. See, the old trick was just to increase the clock speed, basically make the chef chop faster. But when you do that, you generate an incredible amount of heat. We literally reached a point where if we pushed the speed any higher, the chips would get so hot they would melt themselves. So here's the crucial point. We couldn't just go faster anymore. We had to get smarter. And that brings us to the first of two really revolutionary paths forward. While the whole PC world was kind of stuck, Apple made this huge, radical bet. They decided to solve the memory problem by fundamentally rethinking the entire blueprint of a computer. So for decades, a computer was basically a collection of separate parts, right? You had your CPU, your GPU for graphics, your RAM for memory, all spread out across a big motherboard, talking to each other through these relatively slow connections. Apple's approach? They threw that entire blueprint out the window. They built what's called a system on a chip, putting everything, CPU, GPU, memory, the whole shebang, into one single, tightly integrated package. And this is their absolutely genius solution to the memory wall. Instead of that warehouse a block away, they built the entire kitchen right there at the chef's workstation. This is what they call unified memory. The CPU and the GPU aren't just neighbors anymore. They are sharing the exact same pool of super fast memory. No more long walks and a whole lot less waiting. And the results? Well, they speak for themselves. Just look at these numbers. The M1 Pro was already hitting over 200 gigabytes per second of memory bandwidth, but the M1 Ultra, over 800. These are speeds that traditional desktop platforms, with all their separate components, could only dream of. By tearing down the physical walls between components, Apple basically tore down the memory wall. But just as one massive problem was being solved, another, even bigger one showed up. I'm talking about the insane computational demands of artificial intelligence. This wasn't just about making one chef faster. This was about feeding an entire city and doing it instantly. Okay, so to really get the AI hardware revolution, you have to understand this one key difference. There's training and there's inference. Training in AI is like teaching it all of human knowledge. It's this massive, one-time task using huge batches of data. But inference, that's using the AI to answer a question. It needs to be wicked fast, super efficient, and happen in an instant. These are two totally different problems that require totally different tools. It affects everything, from how much data you process at once to the kind of math you use. Training needs really high precision, while inference can get the job done with simpler, faster numbers. So this need for specialized tools created the second major path forward, hyper-specialization. This is the world of hardware that is not designed for general tasks. It's designed for one thing, and one thing only: making AI go faster. NVIDIA's strategy is best described as, well,
beautifully designed brute force. Their GPUs, like the new Blackwell platform, are just packed with thousands of specialized little processing units called tensor cores, and they're connected to this incredibly high bandwidth memory. They are these powerful, flexible engines built to do the really heavy lifting of training enormous, complex AI models for all kinds of different tasks.
Now, Google, they took a completely different path with their Tensor Processing Unit, or TPU. Instead of a flexible engine, they built a highly specialized machine, and at its heart is a concept called a systolic array. It's a fundamentally different way of thinking about how to do math. And that assembly line analogy is absolutely perfect. Data just flows through this systolic array like parts moving down a conveyor belt. Each little element performs one simple calculation, a multiplication and an addition, and then just passes the result to the next guy. Now, it's not flexible at all, but for the very specific type of math that totally dominates AI workloads, it is breathtakingly efficient. So here you have it, the two philosophies side by side. NVIDIA's GPU is the powerful generalist, right? Flexible tensor cores, massive memory, great for a huge range of AI training jobs. And then Google's TPU is the hyper-efficient specialist. Its systolic array is perfectly tuned for scaling up massive, very specific models with just peak efficiency. Two very different solutions for two different ways of tackling the AI problem. And the benefits of all this specialization? Well, they can be staggering. Get this. For certain types of fast, interactive AI tasks, like a chatbot responding to you in real time, the most specialized chips can be over 18 times more energy efficient than their general-purpose cousins. That's not just a little better. That is a revolutionary leap in efficiency. So what does this all mean? It leads us to a new reality in computing. The era of having one single, all-powerful, general-purpose processor is, well, it's over. We are entering a brand new age, and it's going to be defined by diversity and specialization. So let's recap the big takeaways from this whole revolution. First, just getting data to the processor. That's now the most important problem to solve. Second, those two paths we talked about, Apple's tight integration versus NVIDIA and Google specialization, they show this really clear trade-off between flexibility and efficiency. But the most important thing is this. The workload now defines the hardware. You don't just build a generic chip anymore and hope the software runs well. You look at the problem you need to solve, and you build a chip specifically for that problem. Which leaves us with a really fascinating final question. We are building machines that think, machines that can see, machines that interact with our world. So will the computer of the future be a single unified system like Apple's, a kind of jack of all trades? Or will it be more like a collection of hyper-specialized minds, like those AI accelerators, where each one is perfectly designed for its one true purpose? The answer to that is going to define the next 50 years of technology.